Hello, and welcome back. I'm Matthew Lay, and in this presentation, we are going to discuss voltage dividers. So let's get started. We have some objectives. First, we want to define a voltage divider. Next, we want to define a loaded voltage divider, and we want to be able to differentiate between a loaded voltage divider and just a common voltage divider. We want to be able to calculate the resistance values for a voltage divider and for that of a loaded voltage divider. And then finally, we want to be able to determine the wattage size of the resistors based on our power calculations. So when we talk about voltage dividers, we're really talking about two different types. We have unloaded and we have loaded. Okay, we're going to look at the unloaded first. This is the least common. Before we actually dive into the unloaded voltage divider, we want to look at a little bit different way of representing our schematic. So what we have here on the left is our traditional series circuit that we've been working with so far. And what we have here on the right is typically more how we represent a voltage divider. Now, they are actually equal to one another. This circuit here has a common point electrically through this wire that comes over to the negative of our power source. Here we have two grounds. Whenever you have a ground symbol, that they all are referencing the same point electrically. So that means that these two are the same point electrically. So therefore, we could actually draw a line between here. So you might ask, why would we have ground symbols instead of a line drawn between here? Well, this actual branch here could be on page 2, and this could be on page 1. So instead of having to draw a line that references all the way back to page 1, we'll use these ground symbols to denote that that is going back to the same point electrically. Okay, so we just wanted to introduce that to the students. And then here for the voltage divider, we have a node or a point on the circuit that is denoted by the letter A, and that's going to become very useful to us in these voltage divider circuits. So when we look at these two circuits, even though they're represented in different forms, both of these circuits are representing the exact same circuit. Okay, one is a traditional series circuit, and the other one is what we would consider a voltage divider, which is a characteristic of a series circuit. Let's look at an unloaded voltage divider. An unloaded voltage divider is nothing more than just a series circuit. We are representing it in a little bit different form here in our schematic, but it is still nothing more than just a series circuit. So let's look at some terms that we've already reviewed or already discussed. The voltage referencing, E sub A, is nothing more than point A to ground. So that would be like putting my meter with the red lead on point A and the black lead on the ground. And I could put it on this ground right here, or I could put it on this ground over here. Either one, I would get the same measurement because these are the same point electrically. So E sub A is just from A to ground. Okay. To get our voltage drop across R1, all we do is take our total voltage and we subtract this E sub A from point A to ground, and that will get us our voltage across R1. Now this lower resistor, if you notice, the name has also changed from R sub 2 to R sub B, and the reason why is it's going to be termed a bleeder resistor. So the B just stands for bleeder, and we're going to find out why when we get into loaded voltage dividers, why that's called a bleeder resistor. But we're going to go ahead and start the practice of calling that R sub B here in this particular circuit. Okay, so the ERB is equal to EA, because from here to ground is nothing more than measuring across this resistor. We just showed that with the voltmeter. And so ERB equals that A to ground measurement. To get the value of this top resistor up here, all we have to do is take the E1 that we calculated up here and divide it by our total current. Okay, to get the value of this resistor here, we just take I could easily have said E sub A here as well, but the ERB and divide it by total current as well. Why are we using total current in both of those formulas? Because a characteristic of a series circuit is current is common. So the total current that goes through R1 is also going to go through R sub B. Okay. Let's look at a problem where we're going to work out some of these things. So here we have a source that is 10 volts, but I'm sorry, 12 volts, but we actually want to reference at point a 10 volt presence. And so we're going to create this unloaded voltage divider. There's going to be no load. We're just going to have that voltage present. And we want it to be 10 volts. And then we know that our total current, or we're given our total current of 350 milliamps. So let's use the formulas from the previous slide to calculate out our quantities here. So we know E sub 1 equals the total voltage minus our E sub A. So that's our 12 volts minus our 10 volts. That gets us 2 volts across this particular resistor here. And that's how much we needed to drop for us to be able to have 10 volts right here at that particular point. And then we know the voltage across this bleeder resistor is going to be 10 volts. That's a given. So that is 10 volts. And then we can figure out the resistance value of R1 by just taking this 2 volts and dividing it by our given. This is just from our Ohm's triangle. We're going to take 2 volts and divide it by 350 milliamps and get 5.714 ohms. Excuse me. Okay, and then to get our bleeder resistance, we're just going to take our voltage across that bleeder resistor and divide it by our current, and that is going to be 10 volts divided by 350 milliamps, and that will be 28.571 ohms. Okay, so those are our values for an unloaded voltage divider problem. Now, we're not going to do a whole lot of these because these are very uncommon. The ones that we almost always are going to be dealing with is loaded voltage dividers, and that's what we're going to focus on here next. Okay, so here's our loaded voltage divider, and the only difference is we've added a load here, okay? So a loaded voltage divider is nothing more than a series parallel circuit. You can see this is the simplest series parallel circuit we can make. We have 3 resistors. One of them is going to carry total current, and when it does that, that makes it a series parallel. But then it has a minor circuit in it that is parallel in nature, and that's these 2 resistors are in parallel with one another. And then again, we're showing all 3 of these legs going into ground, which means that these are all the same point electrically. We could have easily drawn a line across here, but again, this load could be on page 10, this bleeder resistor could be on page 5, and the power supply could be on page 1. So we use this ground symbol in a large schematic to show that they're all going back to the same point electrically. E sub t is our source voltage, like it has always been. The R1 is now, we're going to actually term this a drop resistor. Okay, so we're going to get used to a new term. We already learned about a bleeder resistor. This is going to be our drop resistor that's going to do nothing more than drop the voltage to where we want it in this particular voltage divider. R sub L is the load. This is going to be the actual load that we're going to put across here. And this is what this voltage divider is actually going to be powering, is the actual load. Okay, so that's our load out there. And then we learned in the previous example, R sub B is known as our bleeder resistor. Okay, and that is there just so we can get the right amount of current through our drop resistor to drop the voltage to the quantity that we needed for our load. As a design premise, we're going to use, and it's not always this way, but in this course, we're going to use a bleeder current of about 10% of total current. Okay. So our I sub B, the current through the bleeder resistor, can be calculated by taking your load current and dividing it by 9. Okay, that makes the load current 90% is going to go through the load, and the other 10% is going to go through your bleeder. That's where that formula comes from. Okay, so now let's actually put this problem to this. Okay, so if we're given 15 volts, but we actually want the load to run off of 14 volts. Okay, and this is very common in the field. You may have a power source that puts out a different voltage than what your load requires. And so your power source is 15 volts. Your load requires 14 volts. So we need to drop a volt before we can actually send it out to our load. Okay, and our load is going to be quite often denoted in how much power it draws. So our given here for our load, P sub L, is going to equal 500 milliwatts. So the load current, I sub L, equals our actual load wattage divided by our load voltage, and those are all givens. So we have 500 milliwatts divided by 14 volts, and that's going to equal 35.714 milliamps. Our bleeder current, I sub L, I sub B is going to equal our I sub L, the load current, divided by that 9. That's just our formula that says 90% is going to go through the load, and 10% is going to go through the bleeder. So we're going to take our 35.714 milliamps divided by 9, and we're going to get 3.968 milliamps of bleeder current. Okay, we can go ahead and figure out the value of our bleeder resistor because we know the voltage across that. Remember, the bleeder resistor is in parallel with our load, and our load voltage was given to us. And a characteristic of a parallel circuit is voltage is common. So in this case, we're going to have 14 volts divided by our bleeder current, and that is the 3.968. And that's going to give us the actual ohm value of our bleeder resistor, which is 3.528 k ohms. Okay, bleeder resistors are typically going to be pretty high in resistance, and we're going to find out that our drop resistors are going to be usually pretty low in resistance. Okay, so now let's go ahead and figure out our our drop resistor value. First, we have to get that voltage drop across there. This is pretty easy. We started with 15 volts. We know our load was 14 volts. We're just going to subtract 14 from 15 and get 1 volt of drop is going to happen across this R1. And then our total current is going to equal that load current plus our bleeder current. Remember, a parallel circuit is a current divider, and the current is divided right here at point A. So the Kirchhoff's current law tells us that the sum of the currents coming into point A has to equal the sum of the currents going out of point A. Well, we only have one current coming into point A. We have two coming out. So here are the two coming out. If we add those together, we get the 1 that should be going in, which also is total current. And that's why this is a series parallel circuit, because at least one component in the circuit carries total current. So our total current is going to be equal to the 35.714 milliamps plus our 3.968 milliamps. And we're going to get a total of 39.683 milliamps. And you can see this is exactly 10% of their total current. We actually just move the decimal point over 1 and we get that value. So we're good with our formula there that we use to calculate 10% of our bleeder current. So now we want to figure out that load resistor value. We're going to take that 1 volt and we're going to divide it by that total current that we just figured out of 39.683 milliamps, and we're going to get 25.2 ohms. And like I stated earlier, load resistors are typically going to be low in ohm value, and bleeder resistors are typically going to be high in ohm value. And that's so we're not wasting too much power in these voltage dividers. Okay? Let's see if we can figure out the different wattage size to get for, we're going to just do it for the bleeder resistor here, but the same principle is going to apply for all resistors in our voltage divider. So first we're just going to figure out our powers. So the P1 is going to equal the total current times our voltage drop across that R1. And so our total current times that 1 volt is going to get us 39.683 milliwatts. Okay, so that's going to be our voltage drop across, our power draw across R1. And then the power draw across our bleeder resistor. Of course, we already know our power draw from our load because it was given. But the last power that we'll have to calculate is across our bleeder resistor. And we're going to take our bleeder current times the 14 volts. It's 14 volts because that's our load and we're in parallel with our load. We're going to get 55.552 milliwatts of heat dissipation in that resistor. Okay, so now this is a design principle that you want to, when you select your actual resistors, you want to double the power of the design for the actual component that you selected. So if we take our 55.552 milliwatts, this should say milliwatts here, times 2, we're just going to double that value, we're going to get 111.104 milliwatts. Well, they don't actually sell resistors in that particular size, but they do sell 1/8 watt resistors, and a 1/8 watt resistor is 125 milliwatts. So that is going to be over even doubling the size of the design power that resistor is going to require. So we're gonna choose an 1/8 watt resistor. Now we could do that up here as well for the 39 milliwatts, but again, the smallest wattage resistor we can get is 1/8 of a watt, and so we would probably pick 1/8 of a watt for that one as well. Of course, if you picked a 1/4 watt, you'd have extra protection there. Okay, so let's review. Define a voltage divider. A voltage divider is nothing more than a series circuit. We show it in a little bit different form, but as far as a simple unloaded voltage divider, it is a series circuit. A loaded voltage divider is a series parallel circuit. The loads are in parallel with the other components in the circuit. And of course, when we do that, we're going to introduce a drop resistor and a bleeder resistor for us to be able to calculate out our different drops for our loads. The difference between the two is we don't have a branch component when we get to the unloaded voltage divider. When we get into the loaded voltage divider, that's when we get into some sort of a combination circuit, and that requires us to understand all the physical characteristics that are associated with combination circuits. This concludes our lesson on voltage dividers and loaded voltage dividers. I hope that was helpful, and we'll see you in the next video.